Hi everyone, my name is Lydia, and this is what I wish they had taught me about econometrics and introduction. In the previous videos, we've talked extensively about OLS and how we're going to use the OLS to find the best fitted line. However, I would like you to remember that while the least squares is a very powerful method, it's not the only method. So there's more than one way to estimate a line. The methods available to you include the squared distances or OLS, the absolute distances or least absolute deviation, which is also in abbreviation called LAD. And to some of you, this question might have become very obvious when looking at the previous video. Why should we use the sum of the squared error where we could take the absolute value of it and that would give us a smaller number to work with? Well, on top of that, there's also other methods like the maximum distances, the quantile loss function. However, the reason why you will be thinking of OLS every time you hear the word regression and why you'll be learning OLS as the very first method before moving on to more complicated methodologies is most of all because it's what we call mathematically smooth. Okay. So why is it mathematically smooth? Because for the squared distances, we have a function that is differentiable. However, with absolute distances, that is not the case. So the least square function being differentiable, it means we can take the derivative, we can set it equal to 0 and solve it like as you solve any other optimization problem in math or even in microeconomics. However, absolute value as a function, and I'm going to show here graphically what the absolute value of x as a function would look like. It's this V shape that has a very sharp corner here at the origins, which means that it's not differentiable at 0. So it means you won't be able to find a closed form solution, which means you will need then linear programming or other types of algorithms to be able to get like an actual closed form solution that makes sense in terms of interpretations and so on. So there is also a very simple way to show you, well, why should we use the square distances? Like, what is really the difference between the two of them? We know that mathematically speaking, the minimization problem that where they are starting off is different, but how exactly do they differ in what they show us? And for this, I have prepared a little exercise with just 3 data points that we can go over. So we're going to use these 3 data points. I'm going to show you the computations, and in the end, we're going to compare how the two lines look against one another. So in terms of OLS computations, I have this very long table. It's not too complicated. What I am doing is mainly computing the average x here and then the average y and then doing the difference between x and x bar, y and y bar, the product, and also x minus x bar squared. And that is because I'm going to be a little bit cheeky in this video and jump ahead by using information that you will be mostly seeing in the next few videos. But I'm going to use the actual formulas for the beta OLS, and that is using the sum of the product here and the sum of the x minus x bar squared, which I have already computed to be 2 over 2, so that means my slope is actually just 1. Then I will use once again a formula for the intercept, and that is going to give me y bar minus beta times x bar, which is simply 1.66666, but we're going to approximate here as 1.67. Now, what that means is basically that my OLS line should look something like 1.67 plus x. Keep in mind, the slope is just 1, but I don't need to write that. Okay. How will this line look? Well, very easy. We've got the intercept alpha right here, and then we can just take a value, let's say x equals to 1, which means my y will be 2.67. So 4.1 in here, I'm going to have, let's say 2.67 is right here, this point, and I simply need to connect these two to have my OLS line. Okay, so this is what my OLS line would look for these particular 3 data points. As you can see, none of our points in here, let's call them A, B, C, none of them is on the actual line, which means like there is an error that you're making in your prediction for each of these 3 data points. However, this line in here best describes the positive relationship that exists between our X and Y in this case. So now that we have figured out the OLS line, let's see what the LAD line would look like. Now, it might be a little bit weird for all of you to think, well, how do I find the minimum or like the minimization of the sum of the absolute value of a particular computation? What we're going to use is finding basically the median of a pairwise slopes, which means every 2 coordinates, we're gonna use them together and find the slope of the line that goes through them. And after that, we're going to do the computations of the residuals for the 3rd point that is left out of this line, and then in the end compare these residuals to see which is the smallest, and then this is the line that we're going to take, because the main intuition is like, if you have 3 points, obviously the one that's going to give you the absolute, in terms of absolute value, the smallest error that you're making is, well, a line that goes through 2 of the points, which means you're making 0 error on these 2 points, and then you've got a 3rd point on which you're going to make, unfortunately, some mistake. So I'm going to show you how to do the computations for the combination of coordinates 1, 2, and 2, 5, using the formula rise over run that you might have seen in your GCSEs. You can easily find that the beta is 3, and the alpha, the intercept, is just -1, which means that the line that we are looking at is y equals to -1 plus 3x, okay? So remember, I was just finding the line that goes through the points A, B. So if I were to connect these 2 points in here together, basically this line has the slope of 3. And if I were to extend it even further down here, basically it would have passed through -1, okay? The 3rd point that is left is this point C, so let us find what is the mistake that we're making on that point. And that is fairly easy to do. So calculating the residuals, keep in mind the residuals for point A is 0 and also for point B is 0 because we're making 0 mistakes. These points are on that line. However, if we are looking at point C, well, point C, the coordinates are 3, 4, which means the x is a 3. Now, whenever the x is a 3, that means that my y is equal to -1 plus 3 times 3, which would make it an 8. This would be my y if I was on that line, but I am not on that line. The y of my c is actually 4, which means that, well, the mistake that I am making is 4 minus 8 in absolute terms, it's equal to 4. So look carefully, we have residuals here 0, 0, and 4, which means that the sum in here is actually 4. If we do exactly the same kind of computations, and I've done those numbers for you guys, so we've got the combination 1, 2, and 3, 4. We're going to have a slope of 1 with an intercept of 1, and the residuals at each point in here are 0, 0, 2 with the sum of 2. So far, this is the smallest one we see, and for 0.25 and 3, 4, we're going to have a beta of -1 and an alpha of 7, which means that we're going to have residuals 4, 0, 0, meaning a sum of 4. So again, out of all of these combinations, it seems that the best line would have been, in this case, a line that looks y equals to 1 plus x. Okay, for the second case where the residual was 2. So let's look at that. So it's a combination 1, 2, 3, 4. So this line would have been the line that goes through A and C. Bear with me. Gonna make this a little bit nicer. So keep in mind, this would have gone through 1 in here as your intercept. So this would have been your LAD best line. Okay, we can draw the OLS line that we found earlier. Keep in mind our Y OLS was equal to 1.67 plus x. So as you can see, the slope is the same, but the intercept here has changed, and we're gonna see. So 1.67 in here, and then we had a point here that we easily found to 67 and connected. So this would have been our OLS line. Clearly the two are different because we had different computations. It does look like they are sort of parallel in here. They are because the slopes are 1 and 1. However, as you can see, the intercept is changing. So what exactly is different between the two methods of estimation? With just 3 points, it's a little bit difficult to really see this is the difference and this is better of the 2 lines to be used. However, if you have more data, that's going to become more obvious. In fact, LAD is not completely useless. It's actually better of a method to use whenever you have outliers or whenever you want a median regression or whenever errors are what we call heavy-tailed. It's definitely computationally heavier, and it came after the OLS as well, so that's why we see the OLS becoming the norm. But that being said, the OLS has also a few other advantages that make it so nice, easy, and elegant to work with, and those characteristics come under the right assumptions being fulfilled. And what I mean is, under the right assumptions, our OLS gives us unbiased estimators, consistent, smallest variance among all the linear estimators. It gives us simple formulas to work with, and it's easy for us to make inferences through the t-tests or even the confidence intervals. So overall, there's definitely advantages to both. However, the least squares is the one that you are going to associate most of the times wherever you hear best fitted line or regression. So to conclude overall, keep in mind OLS is just one estimation method. There are other methods, but this is the cleanest math, strongest guarantee to get to understanding the causal relationship that you want between your X and Y. It's a little bit, as we said, the OLS is is the Batmobile to your Batman. So if the Batmobile is basically built on squares, it gives you like that smooth, powerful, and reliable performance that a Batmobile is associated with. I hope this helped get a further insight into like the different kinds of lines that can be fitted into your data, and I will see you in the next videos.